thing I want to talk about after 4.3, it's not really necessary to do this. This is kind of a neat trick that works sometimes. You can use the second derivative. So this kind of works sometimes. I think everybody would agree that this is a local minimum, right? And this is a local maximum. What can you say about the curve here as far as the concavity goes? Right? At that local minimum, what happens? Smile or frown? Smile. So this is concave up. And this is concave down at the local max. And so this intuitive picture gives me sort of C's for the second case. And what it says is if f is continuous in an interval and f prime is 0. So suppose that I mean, now it's a critical number, but it's in fact a number with a group at 0, not even defined. Then 1 if f double prime of c. So take the second derivative, you can, assuming you can. If this is bigger than 0, then c f of c is a local. Let's see, f double prime of c being positive means it's smiling. This is supposed to be a local limit. 2, if f double prime of c is less than 0, then c f of c is a local max. That means it's frowning. 3, if f double prime of c equals 0 or does not exist, then it equals right. So here's the second derivative test is kind of cool. And I'm not going to prove it, but it, gets sort of the picture, gets the intuitive reason for why that might be true. It's kind of cool, but number one, here's the problems. It forces you to take another derivative. So you got to do that. And here's the problem. Second derivative might not exist, or the second derivative might be 0, in which case the test tells you nothing. It's not going to give you functions when the second derivative is 0, where there's no no local max or min, or there's a local max or there's a local min. So it really is truly inclusive. So why bother if it's something that works? See, the beauty is the first derivative test where we check whether things are increasing. That always works. So why would we care? Because in some problems, so practically speaking, in some problems, especially application problems, especially where it's really easy to take the second derivative, this can sometimes be equivalent in some things. So if your function is very easy to take the second derivative and quickly figure out, it's no problem. But just be aware that this sometimes doesn't work. Okay. Let me start you off on this. This is one of the most important limits in calculus. And actually, it's one of the more important ones in kind of, physics, dynamics, so. What is this one? Probably got this in 1040. This is one. Now notice, with any kind of limit, the first thing to always do is be a bonehead and try to plug in, and I get 0 over 0, right? That is a command from above that there's more work to be done when it's 0 0. Usually with some limit, what are you used to? You're factoring something out, right? You can't factor anything out of sine theta. Does anybody remember how you all showed this? You went to the details of this. What you did was looked at this angle theta. You put this on a circle radius 1. If the radius of this is 1 and the same as theta, then theta corresponds this length here, and this length here is sine of theta. And you did some squeeze theorem kind of arguments to show the limit as theta goes to 0, sine theta over theta is 1. And intuitively, doesn't it seem like this is kind of curvy a little bit, and this is straight, but as that angle gets smaller, these are almost the same thing, straight drop in the vertical circle. Everybody agree with that? And that's essentially the way you evolve the flow, right? But you had to go through all this rigmarole, you had to take it, do some inequalities, set up some limits. And the reason you bothered to do this is you needed this limit to figure out what the derivative of sine and cosine. Remember when you did that, figure out the derivative of sine is cosine, or cosine is negative sine. This limit is central in figuring that out. That's why you needed it. Well, L'Hopital's rule, now that we've kind of matured a little bit and have this background, L'Hopital's rule is a really groovy way to figure out such a limit. We don't have to draw pictures and do inequalities and stuff. Let me tell you what L'Hopital's rule is, and then I'm going to spend basically the day doing a bunch of different kind of examples. It's like be of interest here. There. Suppose, and this is maybe sort of L'Hopital's rule, f of x and g of x are differentiable functions. That just means, hey, I can take a derivative of it. I assume they're differentiable on open interval I. A. And we'll assume that g prime of x is not 0 if x is not equal to a in this interval. So if the limit as x goes to a of f of x of x 0, or the limit as x goes to a of f of x, limit x goes to a of g of x are plus or minus infinity. They can be both plus infinity, one's plus infinity, one minus infinity. So if you get both limits are 0, or both limits are plus or minus infinity, then limit as x goes to a of f of x over g of x. The limit as x goes to a of f prime of x over g prime of x. with a caveat. If the limit a f prime of x over g prime of x exists, or is plus or minus infinity. So that's what we call a rule. It allows you to take a derivative quotient, taking the limit of the derivative. Notice that this is not the quotient rule. This is derivative top, derivative bottom. This also works for a equal plus or minus infinity. So an infinite limit will work on what we call as well. And left and right limits as well. So that is to say, x goes to a plus side, x goes to a minus side. So you, L'Hopital's rule works for left limits, right limits, it even works if a is infinity or minus. Okay. So let's see this in action. By the way, you might wonder why I had freaked out and in doing section 4.7, L'Hopital's rule before we're doing the other intermediate section. That's because the opposite didn't do it wrong. What we're going to do right before the second test is we're going to really focus on drafting functions. We've already done this a little bit. What we've done so far in drafting functions tells you how to find local maxes, local minimums, how it curves, whether it's concave or down. The last thing you need to know about functions is what's their infinite behavior. What happens to the function? It goes off to the infinity. It's go way up, flatten out, go way down, and L'Hopital's rule is necessary for figuring some stuff out. Also, if the function has a discontinuity, you want to know what happens. So let's do some examples, figure out some of these limits. Okay, this is the first limit I put up. Back in 1040, you all probably went through some pain to figure this out, like I said, with the circles and whatnot. Here's how L'Hopital's rule makes magic. First thing to do would be a bonehead, plug in. If I plug in 0, what do I get on top? 0. What do I get on bottom? 0. This is a job for L'Hopital's rule. What's the derivative at the bottom? Derivative at the top. What's that? Just plug it in. L'Hopital's rule is equal to 9. Here's one that you can do the old fashioned thing. Let's and let's say x 17 x 4 plus 8 x 3 minus x squared. Now, let's look at this. Limit as x goes to 1 of this crazy quotient. Now, plug in. That's the natural thing to do. What happens when I plug into the top? If I plug in 1 minus 1 is 0. Plus 6 is 6. Minus 1 is 5. Plus 3 is 8. So I get 0. If I get something other than 0 on the bottom, then 0. See where it comes from. 1 minus 12 is negative 11 plus 8 negative 3 minus 4 is up. I get 0. That means there's more work. Now, you can do this without looking tolerable. How would you do that? Well, you can factor it, right? Because notice when I plug in 1, I get 0, right? That means that this polynomial has to have a factor of x minus 1. When I plugged in 1, I got 0 on the bottom. That means this polynomial has to have a factor of x minus 1. Now, who wants to divide x minus 1 into these and figure out what that other factor is? Nobody, right? That's going to stink. Let's try to look at the top and see what that is. Derivative at the top. 5x4 minus 4x cubed plus 18x squared minus 2x plus 3. Derivative at the bottom. 17x to the 16 minus 48x cubed plus 24x squared minus 2x. By agreement on derivative. Now let's plug in and see. As long as I don't get 0 on the bottom, I'm done. On the bottom, I get 17 minus 48, which is negative 31. 24, so that's a negative 7. Minus 2 is minus 5. See what I get at the top. 5 minus 4 is 1, and 18 is 19. Minus 2 is 17, plus 3 is 3. Okay. Any questions on that subject? That's what the top rule says. The limit, this original limit is, you can make it easier by taking the derivative of time, under the conditions. Now, let me, give you another couple of examples here. Okay. What happens if you're a bonehead and plug in? What do you get in the top? Yeah, you get sine squared of 0, which is, and on the bottom, you get sine of 0, which is 0. This sounds like a job below the top. So let's see. Okay, somebody help me with this derivative here. What's the derivative of sine squared of AX? Right, so this is actually sine of AX, quantity squared, right? So the first thing I come to is blob squared, right? So this should be 2 blob to the first power. Now I've got to multiply by the derivative of blob. What's the derivative of sine of blob? Cosine blob. And I'm still not finished. I can multiply by the derivative of blob, which is Right, the derivative of AX is just what, A, right? Everybody follow this one? I think this one's a little bit easier. The derivative of sine of block is cosine of block. Now, I multiply by the derivative of what I find inside, and what's the derivative of what I find inside? Okay, let's see what I'll do for it. Now let's plug in. What do I get when I plug in x equals 0 to the top? 0. What do I get when I put in the bottom? Yeah. So what do I do now? Correct. Why not? Let's try it again. Right? What we talked, keep it over and over. Tell me what's unpleasant about this. Right, everybody agree with it. Now I've got a product rule that's still a chain rules. This is product rule. Everybody agree with it. I can shorten it. So don't be completely, get out of the box a little bit and think about this. This is 0 over 0, right? Why is it 0 over 0? Well, basically, what's causing the 0 over 0? It ain't the cosine. It's this thing. And on the bottom, it ain't the cosine. It's this. Right. So let me take a look at this. Let's just pull the offenders in. Right, because really, the only thing that's making this 0 is the sine AX. The only thing that's making it 0 is the X. So let's pull these out and do it separately. This is a 0 over 0, and it's much easier to take the derivative of these things, right? So L'Hopital's rule gives us derivative of x is 1, and the derivative of sine AX is cosine AX times the derivative of AX, which is A. So this limit is A. Now let me carefully finish this problem using my side. This is the limit as x goes to 0. Sine AX over X. Now we put everything here. It's not sine AX, so I get 2A cosine AX. And on the bottom, what do I get? 2B cosine BX squared. These are not offenders because I can just plug into this. This thing we found out is A. And this thing I can just plug in, and this is 2A over 2B. So I get A squared. Equals. Okay. First thing to do in this example is to be a bonehead and try to plug in. Well, good luck. Good thing. But would everybody agrees that both the top term and the bottom want to infinity is exponential? So we got this dominant Q. Everybody okay with that? So what Tolkien says, well, okay, this is kind of a first sort of lesson into, just because you've got this powerful weapon doesn't mean you should use it. Right, agree with that? Now, what do we get again? Infinity over infinity? 12x minus 2 is 30x. Infinity over infinity again. And this is whatever this is, 1230 is, which equals what problem is really this? Oh, somebody extract that away. But that's it. It's the measure. You just have to verify. Biggest power vector I see in the top, 3, biggest power vector I see in the bottom, 3. It's a tie. So let's multiply top and bottom. 5, 1 over x cubed. Wait a minute. X goes to infinity. 2 minus 1 over x plus 1 over x squared plus 1 over x cubed. 5 plus 1 over x squared is 7. And as x goes to infinity, all this crap hole in here, 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 all goes in. So there's no real need for it. In fact, it's really not best practice. And you have to be careful. I'm gonna show you kind of an interesting slipping point. What we could kind of list up on. Let's look at the. Anybody look that tell you what the limit is? Let's see what all. Would everybody agree that the top is going to infinity? Right? 3x, as x goes to infinity, is getting cubed. Everybody agree with that? What does 5 cosine x do? Because cosine x, what do you know about cosine x? What numbers is it? Right. So this piece right here is actually, it's very large, it's wiggling back and forth from 5 and -5. Do I agree with that? So when X gets big, X is like, 10 billion, this makes almost no difference, right? Right? So this is going to infinity, and this is going to infinity, right? We can use what we call it, we can write. What is this limit? Right, picture what this looks like. If I graph was 3/2 on the 5/2 sine X, this can be as big as 4, right? 3/2 plus 5. Or it can be as small as -1, right? Here's what this function looks like. -1, 4, and 0. That's that forever. So what's this limit? Doesn't exist, right? As X goes to infinity, this isn't settling down on any, right? It's just completely. So what conclusion do we have about this? When I did the local telephone, I got this thing I got that it doesn't exist. What does this mean about this? This one doesn't exist. This one's actually 3/2. Well, let's go back and read what the lawyers tell us, right? If the limits are both 0 or the limits are both plus or minus infinity, okay, we got that, right? Because the limit at the top, the limit at the bottom was infinity, right? Then the limit of f over g is the limit of f prime over g prime. If this limit exists, or is plus or minus infinity. This limit that we've got, that L'Hopital barfed out for us, is not plus or minus infinity and it doesn't exist. This means L'Hopital does not apply. You got to resort to something else. You got to do something else. So if you do a L'Hopital's rule and you get a DNE, and I mean really does not exist, plus infinity or minus infinity, okay. You get it does not exist. That means L'Hopital's rule doesn't apply. So I did say this is 3/2. How do we do this one then? I mean, if L'Hopital's rule didn't work for us, I'd like to know that something does. Let's kind of rewrite this. X goes to infinity of 3/2 plus 5 cosine x over 2x. Does that help squeeze the answer out of you? If you believe my answer is 3/2, then I guess you gotta believe that this would go to 0. Anybody explain why it does? Okay, so what do I know about 5 cosine x? What's it always between? divide this by two x. And as x goes to zero, times x goes to infinity, one x is 5/2x, as x goes to infinity, goes to zero. Good. And same with the minus sign, right? So what happens to this guy? What variable is? This is equation. So the moral of the story is L'Hopital is a powerful, powerful tool, but you cannot depend on it to be there for you absolutely 100% of the time. Here's one I'd like you all to do. Take a couple of minutes to see if you can work this. 6x minus 6x plus x cubed by 2x. I got an answer for this. I have to do it for you. So let's go through this. Of course, the first thing I always check is to make sure I see if you can load something. If I plug it next to the zero, I get 0, 0, 0 over 2. So still means maybe I should follow the column. What's the derivative of the bottom? Derivative of top. 6 cosine x minus 6 plus 3x squared. Okay. Check it again. Plug in 0, I get 0 on the bottom. On the top, I get 6 minus 6 is 0, and then 2, so I have 0, 0 again. Okay, derivative of the bottom. 40x cubed. Derivative of 6 cosine x is minus 6 sine x. 6 disappears. And this is 6x. Okay. Plug in 0. I get 0. I get 0 on top of 1 on bottom. Then we go again. Derivative of minus 6 sine x is minus 6 cosine x. And derivative of 40x cubed is 120 x squared. So, we did plus 6, thank you, that would change my life, yeah. Plus 6, thank you. So when I plug in 0, I get 0 on the bottom, and I get minus 6 plus 6 is 0. Good. Start again. Derivative of cosine is minus 6 sine x. And now finally, that 6 is, I get 240 x. Of course, I could pull this out with sine x for x, but one more limit. X 0, 6 cosine x over 240, 6 over 240, 1. By the way, if you give me any positive integer, I can set up a little total that will take that many iterations to work out. Okay. What about this one here? Here's an example that's really kind of an application. But n equal 1, 2, 3, any positive integer. I call this example e to the x beats any polynomial. And this is actually an important thing if you're an engineer or scientist, know about growth rates of certain functions. The exponential curve, you all know what this looks like, right? It just goes up to the right pretty hard. I don't care how big your exponent is, you can have x to the 10 billion power. X to the 10 billion power is bigger than the exponential for a while. no matter how big that exponent is, the exponential, the e to the exponential catch it and totally smoke it, always. Look at the limit as x goes to infinity, x to the n of x. Right? Infinity over infinity, right? This is a job for L'Hopital's. Now, take the derivative of x n and use n x n minus 1. Agree? What's the derivative of e to the x? Keep the x. Save the look. Now, if we're down to the 0 power, then this limit is 0. If not, if n is at least 2, then there's still some factors of x up there, right? Do L'Hopital's rule again. N at n times n minus 1, x to the n minus 2, dx. Now, if n is 2, then that's just a constant over e to the x, you get 0. And if not, you keep going. And eventually what you get is the limit is x goes to infinity. If you apply L'Hopital's rule n times, you will get this. And although this may be a big number, you all know what n factorial is. Notation. Are you guys all familiar with this? Okay, well, this is an important notation. It'll come up in 1080 when you power series. You see the button on your calculator. So basically, you just count down, multiplying on the way, and you get 1. Stuff will grow very fast. Oh, and 0 factorial equals 112. This is just a notation. There's no, this makes some formulas convenient. There's actually mathematical reasons why we might define it this way, but this is just notationally, whenever this is 0 factorial, it's assumed it's 1. How many of you have seen this before? Well, of course, this is what you get here, right? For example, you get, what did the limit is x goes to infinity of x to the 5 over e to the x. The limit is x goes to infinity of 5x4 e to the x. X goes to infinity 20x cubed over e to the x. Limit is x goes to infinity 60x squared over e to the x. Limit is x goes to infinity 120x e to the x. And finally, the limit is x goes to infinity of 120 over e to the x. Now, this number here might be very big, but it is, after all, just a number. And e to the x, the number's not moving. But as x goes to infinity, e to the x is arbitrarily large. It's 0. There's a moral to take from the story, because what that means is if you divide any polynomial by e to the x, the limit as x goes to infinity is 0. That means that way out there, if you get far enough out in x, this is tiny. It is incredibly tiny compared to the x. On the other hand, what about this? Actually, exponential grows faster than any power backs. Log grows slower than any positive power backs. So actually, all you really need is in bigger than zero, it's not a five. And in fact, it's this way. What's the limit as x goes to infinity of log x? Well, if you recall, the natural log of x is something like this. And it goes to infinity as x goes to very, very slowly. Positive power of x, x is 1/2 power, x is 1/3 power, whatever, they all go to infinity slowly. So infinity over infinity, let's try what we know. Derivative of x to the n is n x to the n. And what is the derivative of log x? Right, I'll write that this way. Do I agree with that? Multiply, so don't, again, this is another instance where, don't just be, totally bamboozled by, little house rule, do some algebra, to clean things up. Let's multiply top and bottom by x, like with the teacher. And this is the limit. X goes to infinity of 1 over n x. Now, the numerator, this is 1. What's the bottom going to? The bottom's going to infinity, because again, you got positive power there. So this goes to 0. So just like the exponential beats any positive power of x, any positive power of x beats the logarithm, right? Because what's going on there is even x to the 1 over a billion power, very tiny positive power, will eventually beat the log. It'll outgrow it. Any questions? There's another. How about this? Let me look at those. Why is x going to 0 from the positive side? Because it doesn't make any sense to put in negative values for log. Can't come in. Like it's a log of it's positive. Okay, let me be a bonehead plug in. Look at this is a product, right? X or log. As x goes to 0, x is going to 0. So this piece is going to 0. This piece is going to negative infinity. So what do you have? It's hard to say, right? Because here's the problem. It depends on whether x is going to 0 faster than log is going to negative infinity. When you have 0 times infinity, you can have anything. You like any of it. Well, I'll make a 0 times infinity have a limit of 12. Let's say x is 0. feel like such a tool. But this limit is 12, right? Because it's just a limit of 12. But I can break it up this way. This piece is going to 0. This piece is going to infinity. Well, right. Because what's happening is x is getting very, very, very small, positive. This is getting huge. So here we have infinity times 0 is 12. I can have infinity times 0 be 0. I can have infinity times 0. Infinity, and I can have it be any number of 4. So I'd like to use local with this. Unfortunately, local specifically designed for fractions. And this is a product of two things. That's sort of the idea. Here's the thing. This is, so funny in calculus how much you need the algebra. This is a fraction, like we need for local. Freaking make it one. That's algebraic equivalent, and now I have it in a fractional form. What happens is x goes to 0 from the positive. This thing is going to negative infinity, and this is going to infinity. So I've got an infinity over an infinity. So I'm good to go. Let's see if L'Hopital's rule works. Derivative of log is 1 over x. Derivative of 1 over x is minus 1 over x squared. Everybody okay with that? Now, don't go, so this is now you're going to infinity and minus infinity. Don't do that. But this is, I can't stress this enough. In these problems, pay attention to your steps. And if you can do any algebraic cleanup, then do that. You remember that second problem we did when we took out the stuff that was only making things be 0, but doing that kind of thing will help work a lot. Let's multiply by top and bottom by minus x squared. So this is the limit as x goes to 0 from the positive side. On the bottom, I get 1. So basically, I get minus x. Everybody agree with that? And this limit, even I can do it. So it looks like 0 wins the day on this one. Here. Here, I'll put it here. Let's look at the limit as x goes to infinity of 3x and sine of 4 over x. Okay, first thing to do, be a bonehead and see if you can get away with it. As x goes to infinity, this piece goes to infinity. Agree? What about this piece? Well, forget the sign for a moment. As x goes to infinity, where's that go? 0. Everybody agree with that? What's the sign of 0? 0. This is an infinity times 0 problem. So what happens? Let's get this world. I have the same problem I had before. It's probably two things. Geez, I wish this were a fraction. Oh, I wish it was a fraction. Well, I'm going to use my algebra prestidigitation. I'm going to get out Gandalf staff here to turn this into a fraction. How about that? Everybody agree that's algebraically equivalent? And what do I have now? I have 3 sine 0 over 0. So this is an honest to goodness over. Derivative of 1 over x, that's x to the minus 1 power, it's minus x to the minus 2, minus 1 over x squared. Got 3. Derivative cosine of blob. It's derivative sine of blob is cosine of blob. And now I've got to take the derivative of what's inside, which is minus 4 over x squared. Now the minus 1 over x squared can cancel. I get 3 cosine 4 over x times 4. It's 1 over minus 1 over x squared is canceled. This should be 3 times cosine of 0, 4, because this is 1, 0, 12. So that's how you do local tolerance rules. Sometimes if you've got a product, you give a product to two things, you get 0 to b. You say, well, I think we'll wait to turn it into a fraction. Sometimes, okay, so let me what's this? Uh, sort of, but can you go look at this? Ask yourself, what happens to this when it's very, very large? This is very, very large. This is also very, very large. Positive. It's a thing. This is straight up. Don't overthink that. But what if I do this? What if I make this change here? Now it's not so clear, right? This is getting very, very large positive. This is getting very, very large negative. So very loosely speaking, what you have is infinity minus infinity. And what's infinity minus infinity? It could be infinity, it could be minus infinity, it could be 0, it could be 43. It's anything goes. So how do we tackle this? And this looks even harder than what doesn't it? Because the problem here is it's doesn't like put the fraction at all. So what can we do? Well, the philosophy is something similar to what we got before. Let's make it a fraction. And part of the confusion is where we go step square root. Y'all remember doing the conjugate? Let's try that. Let's multiply this by two x plus square root of 4x squared plus 5x plus 1. The idea is just to square out both of these pieces, get all that crap out from under the rack. Now, remember, folks, this is algebra. So if I multiply this thing by this, I better put it in the denominator as well. But okay with that? Think of these black factors just canceling. And so this is the same thing. But okay, so let's see what happens here. In the bottom, I've just got this new factor out in. And in the top, I have 4x squared minus the square of this. So this is limit as x goes to infinity of 2x and in the top, if I clean it up a little bit, I have minus 5x minus 1. Then you can use all of this, and I encourage you to try it. Is everybody with me? So, but I discourage you to work. Right, I'm going to take a page from what Richard was saying earlier. What is the highest power that you see on top? X to the first power. Everybody agree with that? What's the highest power on the bottom? Well, it's x to the first sort of, and it occurs twice. There's x to the one right there, got that. And this is x squared square root. So this is basically first power there. I'm going to multiply top and bottom by 1 over x. This is the sort of top power I see. And this is the limit as x goes to infinity. Minus 5 minus 1 over x on top. On the bottom, this is going to be 2. And I need to slide it under here, so I'm going to rewrite this way. So this is going to be square root of 4 plus 5 over x plus 1. Now, as x goes to infinity, this goes to 0, and these two last terms in the square root go to 0. And so I get minus 5 over 2 plus the square root of 4, which is minus 5. Let me give you a challenge problem. I'm going to change this just a little bit. Do my original problem that I had up here. Notice that when x went to infinity, this goes into infinity. I said, oh, but now if x goes to minus infinity, this is going to minus infinity, and this is going to plus. See if you can figure this out. It's almost the same trick that we get here. You have to be careful at this step here. When x goes to infinity, one over x is one over the square root of x squared, right? If x goes to negative infinity, is this true? It can't be. I'll tell you what. Let's get close to negative infinity, makes it very, very large. What can you say about the sign, S-I-G-N, of one over x? It's negative. What can you say about the sign of the same on the right side, always? Always positive. So if x is going to negative 10, you need to make that adjustment. Now they're equal. If x is negative, then that's what you. There's actually another name for the square root of the square of something. It's the absolute value. That's why you gotta be careful about this. Okay, see if you can work that one. There's sort of one more class of examples that we need to look at, and this is this class of L'Hopital's rule problem comes from variable base. Variable base. And these are the hardest to deal with, but we're already armed with what we need, the log. Right? So let me do some examples. There's an old fun function. This is more important we look at in the logarithm differentiation. This function is defined for x greater than 0. So what happens is function is x is close to 0 from the positive side. And again, this is only defined on the positive side. That's why we can't come in negatives. What is 0 to the 0 in this case? 0. It's 1. Maybe it's something else. It depends on how these two are running the base. How do we do this? How do we do this? Well, notice that I always do it this way. Everybody agree with that? Get a little bit e log key, right? How does this help? So this limit is actually limit as x goes to 0 from the plus side of e to the x log x. Agree? So notice, forget the exponential for a minute. This is going to 0, this is going to negative infinity, right? So what I always do here, find where exponents and plug in. So and we've already done this problem. You might remember what we got earlier. Got this one. No, actually, we got 0. This was actually 0. So this 0. So the limit as x goes to 0 from the positive side of x log x. I'm sorry, of x is 1. Here's another one. I am going to use the previous example. If I did this from scratch, I'd have to do a little bit. I'm going to use the previous example. So this is the limit as x goes to 0 for the positive side of e x to x log x. So this where does this one go? Y'all should I be able to tell me what this one gets. What's that name? Well, this piece right here is going to what? That's our previous problem. This piece goes to 1. Where does this piece go? What else? The natural log x as x goes to here. This might be useful for the next couple. So where's the natural log x to? Close, negative infinity, right? It's actually going down, right? So the natural log of x goes to negative infinity. And that's actually, that distinction is very important. So if this piece is going to 1, and this is going to negative infinity, the whole shebang should go to negative infinity, right? There's no ambiguity. This ain't a 0, it's a 1. Right? So, what should this limit be? The exponent here is going to negative infinity. Look at the graph of e to the x. What happens to e to the x goes, this argument goes to negative infinity. Good. I will guess this one. In fact, see if you can do this. If you have an even number of x's stacked up, it goes to 1. If you've got an odd number of x's, that's kind of interesting. Let's see if you can show it. Okay. Here's another one. How about this one? So the limit x goes to 0. I want you to just, I want you to just look at this. Actually, it's hard to tell, let's go to awesome. Just think about this. What's the base getting close? Like, it's very, very close to zero. What's the base? Two. This is very close. How about the exponent? What's happening? X goes to zero for posits. That's the point. What this is x goes to zero for posits. I'd say 6.10, 100, 1,000, 1/1,000,000, etc. This exponent is a huge positive. What happens when you take two to a bigger and bigger positive power? How about this? This is very similar because the base again is getting very close to two, right? I agree with that. What's happening to the exponent? It's huge, huge, huge negative. What happens when you take two to a more and more negative power? Right, this is actually going to huge. What about this? Let me change this a little bit. What if I go, what happens now? What happens now as the as x is close to zero? What's the base going to be? This time the base is getting close to one, right? As x goes to zero, the exponent is getting very, very large positive or very, very large negative, depending on which side of zero. Right? So you've got a huge exponent, at least with respect to absolute values, huge positive, huge negative. But the base is getting closer to one. What does that mean? You were right not to answer because I don't know what that means either. One to the infinity power. That could be a number of things. It depends on who's winning the race. This sounds like a job for the notice that. Go on the side here. Here we've got the variable base, variable exponent. Yeah, first of all, let me make sure you all see the distinction here because the base is two. Two to a very large power that's going to infinity, two to a very large negative power that's going to zero. But one, it's not clear because when you take large powers of one, it's just one. That's the distinction. This is e the log of 1 plus 2x 3 over x, which is e the 3 log 2x over x. So this can be rewritten as using our stuff logs e to the 3 log 1 plus 2x over x. So our task to solve this problem, we're going to take a little aside here. Find where that exponent's going. Three log 1 plus 2x over x. Okay, so now this is looking like more familiar local calls rule. Let's see, when I plug in 0 to the bottom, I get 0. When I plug in 0 to the top, I get 3 log of 1, and the log of 1 is 0, so I get 0. Let's do local calls rule. This is 1 on the bottom. This is 3, 1 over 1 plus 2x. And somebody tell me, what's that limit? All you gotta do is plug in, and what do you get? This gives you 6. Plug this in. Get about 1, 3 times 1. And this takes us back to our answer. This should be E6. That way. Okay. Any questions? Okay, so what we're going to do, so we've got, I believe we've got the day off. So when we next convene, this is why. When we next convene, what we're going to do is section 4.4, which is curve sketching. Here's the good news. There's nothing new in this other than just the experience of doing it, right? So, go over the local cultural section today, work those problems, and then start doing the curve sketching. I would advise you to do some of the problems before we get together. I'm gonna spend basically all day getting our hands started working with some curve sketching. And then we'll have a review session before the exam as well. Okay, any questions? Well, I will give you all the quiz now.